So we have completed the chapter 4, two-dimensional kinematics. Now we'll explore the next chapter, Newton's laws of motion. And in the current video, we will understand force, mass and Newton's first law of motion. So let's first understand two important quantities in physics, force and mass. Okay, so first term that we're going to see is the force. Now simply speaking, force is a pull or a push. When you are pushing an object or when you are pulling an object, you are applying force. Like here, this person is pushing the object and this person is pulling the object. Now the force is characterized by two quantities. The first one is the magnitude, or what we call the strength, and the next one is the direction in which you are pulling or pushing. Thus the force is a vector quantity since it has both magnitude and direction. Now at a given time, an object is acted upon by several forces. Like here, if you see, the book has a downward gravity force and a horizontal force due to your push and pull, and also the force acted upon by this floor onto the book in the upward direction. So the total or the net force exerted on the book is the vector sum of the individual forces acting on it. And we'll further explore the vector properties of force in the coming few videos. Now let's jump to the next topic, that is mass. The second important quantity in the Newton's laws of motion is the mass of an object. Now mass is the quantity of matter contained in an object, and mass determines how difficult it is to move an object if it is at rest, or to bring the object to rest if it is moving. For example, here you have two objects. This is a tennis ball and this is a heavy stone, and you want to throw these objects into the air. Now clearly in this case the required force is less, and in this case the force involved is much higher. Thus the greater the mass of the object, the more the force is required to change its motion. Now we are all set to explore the Newton's first law of motion. So let's start the first law. Okay, now we'll study the Newton's first law of motion. Now many students around there thinks that force is required for an object to move. That's not true. In fact, according to the Newton's first law of motion, a force is required only to change an object's direction. Now here you see a person pushing a box forward, and as a result of it, it starts moving in the forward direction. As soon as he stopped pushing the box stopped moving. Now when he stopped pushing the box, it's not true that it stopped moving because there is no force acting on it. It stopped due to the frictional force present between the box and the floor. Right? Now let's understand that what happens if there is no friction. So here we have this cart which can slide over this air track, and this is the side view of the air track. Also there is virtually no friction between the cart and the air track. So a cart at rest on a level track will remain in rest unless you apply a little force on it. Now after pushing the cart in the forward direction, it starts moving with a constant speed in a straight line until it hits the bumper at the end of the track. This is the bumper. Then the bumper exerts the force on the cart and causing it to change its direction of motion, and the cart start moving in this direction, in the opposite direction. Now think what would happen if this track is infinitely long with perfectly frictionless surface. Now in such a condition, the cart once set in motion would simply moving with a constant velocity forever. And Newton's first law of motion summarizes these observations in the following statement. It says that an object at rest remains at rest as long as no net force acts on it. Or an object moving with constant velocity continues to move with the same speed in the same direction as long as no net force acts on it. So this is the statement given by the Newton's first law of motion. And Galileo was the first person to articulate the Newton's first law of motion, also known as the law of inertia. The concept of inertia was given by Galileo. And inertia is the property of matter due to which it will not change its motion unless forced to do so. For example, an object at rest, it won't start moving on its own. Or if an object is already moving with some velocity v, it will not alter its speed or direction unless a force causes the change. Hence, the inertia was introduced by Galileo. Now, according to the Newton's first law of motion, being at rest or moving with constant velocity are actually equivalent. To understand this, let's consider this example. So we have two persons, one standing on the ground and other person sitting in the moving train with a constant speed v. Now the person in the train places an ice cube on the dinner tray. Now from this person's point of view or the person's frame of reference, the ice cube has no net force acting on it. Since from this person's point of view, the ice cube is at rest, so net force is 0. Now from this person's point of view, the ice cube has no net force on it and moves with a constant velocity. So for both the person's frame of reference, Newton's first law is valid. And in this example, we can say that each observer is in the inertial frame of reference. That is the frame of reference in which the law of inertia is valid, or the first law of Newton is valid. So if an object is moving with a constant velocity in one reference frame, it is also possible that the same object is in rest in another reference frame. So it's all relative to the frame of reference the object is viewed from. This gives us more compact statement of Newton's first law, and it is, if the net force on an object is 0, its velocity is constant. Now let's understand the non-inertial frame of reference, and to understand it, we'll take the same example. So suppose the train that was moving with a constant velocity suddenly stops by applying brakes. Now from the point of view of the observer in the train, there is still no net force on the ice cube. However, because of the instant braking, the ice cube flies off the tray. That is, the ice cube continue to move forward with the same velocity it had before, while the train comes to rest. So to the observer in the train, it appears that the ice cube has accelerated forward, even though there is no net force acts on it, which is the violation of Newton's first law. Thus, accelerating train is not an inertial frame of reference, and we call it the non-inertial frame of reference. Further, Earth is considered to be the inertial frame of reference, since the acceleration of the Earth's surface is negligible. So this is all in this video. Now next we'll start with the second law of motion in the next video.